This video presents a toolset named ALPACA. Before explaining this acronym, let's see what ALPACA does. ALPACA combines the information computed by may analyses and must analyses to give a comprehensive view of some property's reachability within a C program. Consider a program as an execution tree, where nodes are the program's branch points and edges are the branches taken. A must analysis reports on reachable paths that must hold. They are exact. A may analysis examines a set of paths, and its reports may hold, or they may return a false positive. But when a program subtree is arbitrarily large, a may analysis can safely declare unreachability within this subtree. By combining the exploration efforts of must analyses and may analyses, ALPACA gives a bird's-eye view of how all program executions relate to a property. To do this, ALPACA uses the framework of an alternating conditional analysis, or ACA. ACA takes as input a program and a property, and returns a logical characterization which relates the property's reachability to all program states. We call this structure a comprehensive state characterization, or a CSC. ACA iteratively collects this logical description by running multiple analysis tools, characterizing their results, and blocking already seen paths until all of the paths have been accounted for. ALPACA is an implementation of ACA written in Haskell. We chose Haskell because it allows us to concisely express the core algorithms behind ACA. The top-level routine is shown here. ALPACA is a command line toolset that can be downloaded from the displayed link and installed on a Linux machine. Assuming you have ALPACA installed and are in its base directory, you can list the directory contents and will find a file named demo.c. Before running ALPACA over this program, let's see what's in it. ALPACA will search for the reachability of the call to verifier error. The two first lines declare that the tool analyzing this program will provide a function that implements the semantics of an assertion violation and a function that returns an arbitrary integer value. ALPACA's only required argument is a C program. On the upper right of the screen, we will display demo.c, and on the lower right, we'll track ALPACA's progress through the ACA algorithm. Okay, let's run ALPACA. Each iteration begins by running a portfolio of tools in search of a path to the verifier error statement. The tool portfolio contains 14 state-of-the-art verification tools, some employing may analyses, some employing must analyses. ALPACA checks if any of the tools found evidence confirming or denying the reachability of the error statement. CPA-SEC finds evidence for a reachable path. The evidence given by CPA-SEC is used to perform a directed symbolic execution that logically characterizes this path, namely, when x takes on a value less than 0. The comprehensive state characterization is updated with this path, rewritten in a canonic form. For details about partitions and bounds in a CSC, refer to the technical paper listed at the end of this video. Now part of the state space has been characterized. To characterize the remaining space, the parts that have already been covered are blocked from future analysis. ALPACA does this by instrumenting the program with assume statements. Since it is now known what happens when x is less than 0, the tools are asked if the statement is still reachable, assuming x is not less than 0. On the second iteration, the tool portfolio is launched on the instrumented program. This time, there is evidence of unreachability. Now that all the state space has been accounted for, ALPACA terminates and reports the comprehensive state characterization. In this example, the characterization exactly describes the input space leading to the error statement. More complex cases are dealt with in the technical paper. For a full list of configuration options, run alpaca-h. To try out ALPACA, to access its source code, or to read about its internals, follow the displayed references.